saying a few words about absolute value today, shall we? And then we'll go from absolute value, and that will lead right into some inequalities that deal with absolute value. And in that way, we're going to rely on what we were doing in yesterday's lesson. All right? So let's start out here with what we mean by absolute value. Again, I hope that this is all of a review nature for you. If I were to write these two parallel bar symbols with the number 5, I think we have interpreted this as the absolute value of 5 is equal to some number. And of course, in this case, that number is, is equal to 5. Suppose I were to ask for the absolute value of negative 5. And what then is the absolute value of negative 5, Rick?
5.
It's equal to 5 also. Let me put in another step there in which it's really the opposite of negative 5. And of course, the opposite of negative 5 is the number 5, okay? And in fact, I think from what I have written there that we can generalize this. So let me say that for every a in the set of real numbers, and now let me write what is meant by the definition of the absolute value of a. And in fact, we may write the definition in two parts depending upon what that number a is. The absolute value of a is equal to, and it's equal to a if, and now what can we say about this number a? If, Bill?
A is greater than or equal to 0.
A is greater than or equal to 0, and the absolute value of a then is equal to the opposite of a if, and now what may we say, Doug?
A is less than
If a is less than 0. And this indeed is our definition of absolute value right here. Okay? Well, from this notion of absolute value, let me look at a few other, which turn out to be theorems, but I'm not really concerned about their proof at this time. Well, suppose I were to ask you for, say, the absolute value of 5 minus 3. And we know that this then is equal to, and anyone? 2. Well, in fact, let me write there the absolute value of 2, which we know is equal to the number 2. Suppose I were to write the absolute value of 3 minus 5. And we know that this then is equal to the absolute value of what number here, Dick?
negative 2.
Of negative 2. And of course, the absolute value of negative 2, Kirby, is 2. And so you look at the first line, it's equal to 2, and you look at the second line, it's equal to 2. Therefore, you conclude that the absolute value of 5 minus 3 is the same as the absolute value of 3 minus 5. And in fact, I think you can generalize this by saying for every a and b belonging to the set of real numbers, the absolute value of a minus b is then going to be equal to, and what is our conclusion, Don?
The absolute value of b minus a.
The absolute value of b minus a. All right? There's a third statement that I think that we can look at. Suppose I were to look at the absolute value, say, of 3 times 5. All right? Now, of course, we know that 3 times 5 is 15, and here we have the absolute value of 15, which we know is equal to the number 15. Is that right? Now, let's look then at the absolute value of 3 times the absolute value of 5. And what then is the absolute value of 3? We know that it is 3 times the absolute value of 5 is 5, and of course 3 times 5 is 15. So again, you conclude that the absolute value of 3 times 5 must therefore be equal to the absolute value of 3 times the absolute value of 5. And you think we can generalize this statement for every real number a and b? And here we have for every a and b belonging to the set of real numbers, the absolute value of a times b is equal to, and what may we say? Malcolm?
The absolute value of b times a.
All right, the absolute value of, well, Tom?
A.
Absolute value of a times the absolute value of b. All right? In which here we have the absolute value of the product of two numbers is equal to the product of their absolute values. And this, in fact, is a true statement. All right? Well, let's use some of these ideas in order to start looking at some examples of both equations and inequalities that involve absolute value. Let's first of all look at an equation such as the absolute value of x is equal to 2. And we look at that and we say to ourselves, what number or numbers over the set of real numbers will make this true, Doug?
2 and negative 2.
2 and negative 2. And you say, well, I think I know that. That's not a very difficult idea to understand. Now, what I'd like to do is to shift the emphasis just a bit and write this as the absolute value of x minus 0. And I think you will agree that this is equivalent to the original sentence. And what I'd like to do is to look at it from the point of view of a graph. from the number line. And let's think of this, well, let me make a number line first of all, 2, 3, 4, and so on. Well, -1, -2, -3 in this direction. And let's now think of this as the distance. Think of this as the distance between x and 0 must be equal to 2 units. All right? So here we have the number 0, and the distance between x and 2 must be equal to 2 units. So what then? The number x must appear at this point, so I think you will agree that this point must be on our graph. Similarly, the distance between x and 0, is that right, must be equal to 2 units, can take us over here to what point? And there is our point of -2. So right from our graph here, we may write our solution set as -2, 2. All right, let's look then at another example. Instead of having, say, the absolute value of x, let's write the absolute value of x minus 1 is equal to 2. Now, from the first one, it was quite obvious just by looking at the sentence what the solution set was, but I think perhaps without making it too complicated, perhaps one's intuition fails. So again, let's look at the number line, and here say is 0, 1, 2, 3, 4, and so on to the right, and -1, -2, perhaps that should come out a little bit, -3, should be far enough to the left, all right? Now, again, let's think of this as the distance between x and 1. All right, so here is the number 1, and the distance between x and 1 must be 2 units. So therefore, where must x be? But at what point, Doug?
3.
At 3. All right, so here we have a closed circle at 3, and of course, we may go 2 units on this side of the number 1. Is that right? The distance between x and 1, which indeed is this distance both here and here, must be equal to 2. And that then puts us at this point. And now we may write, immediately, we may write our solution set as, what, Chuck? Charles?
-1.
And here we have -1,
3.
comma, 3, and we're done. All right? Let's look at another example and see what we may say about that. Suppose we had the absolute value of x minus 1 is less than 2. All right, and again, let's go right to a graph. And if we were to make a number line here, there's 0, 1, 2, 3, 4, and so on, and -1, -2, -3, and so on here. Now, here we may think of this as the distance between x and 1 must be less than 2. And again, our starting point, so to speak, is at 1, and we may go away from 1 at most 2 units. And so at the number 3, we're going to have what? An open circle, and of course we then must go on the other side of the number 1 to the left, and that's going to put us at what point, Herbie?
-1.
At -1, and what then are we going to have at -1?
No, sir.
An open circle, and now since we're talking about less than 2, what then is our graph going to look like? And Brenda?
A heavy line between.
A heavy line between, and there is our graph. Now, right from that graph, we may write our solution set. And let's write it as a set of all x's such that, and now let's see what we may say. X is greater than -1, and, right, we must use the word and here, x is less than 3. All right? By the way, what was the fancy word that we used for the word and? Does anyone remember that with respect to our some of our sentences earlier, Don?
Conjunction.
The conjunction. Conjunction, C-O-N-J-U-N-C-T-I-O-N, the conjunction of the two given sentences. Let me take this solution set and write it in a slightly different pattern. Suppose we talk about the set of all x's such that x is greater than -1, and let me put a closed brace on that side, and now here we have the set of all x's such that x is less than 3. Now, if we want to say that this set is equal to this set, now I have two sets, and there's a symbol that I think you learned that we may put between these two sets, which is the same in terms of our sentences as the word and Tim?
Upside down U.
An upside down U symbol, good, which we have given a special name called, Rick?
Intersection.
That's the intersection. All right, I-N-T-E-R-S-E-C-T-I-O-N. The intersection of the two given sets is that set of elements, in this case these points, which are between -1 and 3. Okay? Well, in fact, I think there's one other way in which we may write this set, and it has to do with an idea of betweenness. It's the set of all x's such that, and if I were to put the variable x between -1 and 3 in this fashion, I think you then will agree that we may read this as the set of all x's such that x is between -1 and 3. Okay? And we may do this with the intersection of the two sets and their conjunction, but we can't do that with the disjunction, which in fact perhaps we should look at an example on that. So let's look at an example such as the absolute value of x minus 1 is greater than or equal to 3. And let's see what this graph is going to look like. Let's go right to the number line. So here's 0, 1, 2, 3, 4, 5 to the right, and so on. And -1, -2, -3 to the left, and so on. And now what's our starting point? 1. And we then want to go how many units away from the number 1?
3.
At least 3, is that right? So here we are at 1, and there's 1, 2, 3, and so at least 3 units is going to put us at what point? And
4.
Tim, at the point 4, and this is going to be a closed circle, is that right? And the fact that we're not talking about those elements which are, this distance must be greater than or equal to 3, is that right? So what then are we going to put on our graph? And Doug?
A solid line to the right of 4.
A heavy line, a solid line to the right of 4 with an arrow on it to indicate that goes on forever. And of course we then may go on the other side of the number 1, 3 units, and that then is going to bring us down to this point, 1, 2, 3 to the left. And what point is it going to give us on the left side of our starting point, Dick?
Closed dot at -2.
A closed dot at -2, and
A heavy line to the left.
and a heavy line to the left, indicating that the graph goes on forever in this direction. So let's then write our solution set as a set of all x's such that x is less than or equal to -2, or x then is greater than or equal to 4. All right? And again, does anyone remember what this word was, Bill?
Disjunction.
The disjunction, disjunction, the disjunction of the two sets. And let's then write this by means of two set symbols, a set of all x's such that x is less than or equal to -2, and then we may have another set of all x's such that x is greater than or equal to 4, and the symbol that we invented in order to be able to talk about these two sets, Doug, is what looks like a U symbol, and the name that we have given that is, Doug? The union, U-N-I-O-N, the union of the two given sets. And there's a nice analogy between union of sets and disjunction of sentences, as there is over here of intersection of sets and the conjunction of two sentences. And I think that is an easy analogy to carry through. By the way, notice here, when we have the union of two sets, or else the disjunction of two sentences, we cannot write another set symbol here, another equality symbol rather, in order to be able to talk about betweenness. So every time you're dealing with or the disjunction, or the union, in which you're talking about points outside of some set of points, then in fact you cannot talk about between, all right? It has to be either greater than something or less than something in order to be able to have that idea. Let's look at another example. In fact, let me just make up some simple little case. A set of all x's such that x is greater than or equal to 2, all right? And let me now take or intersection, a set of all x's such that x is less than or equal to -3. And looking at these two sets, since I have here their intersection set, what then is your conclusion about this intersection? I want all of those points which are greater than or equal to 2 and less than or equal to -3. Peter? It's the null set, and the symbol that we have used is this one. There's another word that our text uses and other books also use called disjoint. The two sets are disjoint. There's another phrase, another word that is used. Does anyone happen to remember another one?
Oh.
Well, let's see. Now, we use the word empty set to refer to the fact there are no points there. The null set, and in fact, we may also say that these two sets are, there's another fancy phrase of non-intersecting. Perhaps the phrase that you have not thought about is mutually exclusive. It's It's a mathematical phrase, not a sociological one. Let's look then at another example. Oh, for example, let's take the absolute value of x plus 1 is less than 2. Now notice here in this case I have plus 1. And all of the other examples and everything that I've been saying has to do with the difference between 2 points. So what I'd like to do is to rewrite this as x minus something. And of course, what must this something be in order to make it equivalent to x plus 1?
Negative 1.
X minus a negative 1 must be less than 2, and you're right back in the same ball game. Because let's see, here's 0, and we have 1, 2, 3, 4, say to the right on our number line, and negative 1, negative 2, negative 3, negative 4 to the left, negative 1, negative 2, negative 3, negative 4, and now what's our starting point? Negative 1, and how many units are we going to go away from negative 1? 2 units, and I think that then is going to bring us over to this point, which is what number? Open circle at 1, and also an open circle at negative 3, and the fact that we're talking about is less than, what then do we want, Doug? A solid line in between, which will be these points here, and we may write this as a set of all x's such that, oh, let me use the between the symbol, in which x then is what? Less than 1 and greater than negative 3 would then be its solution set. Is that right? Let's do a few more examples. So let's suppose we had a situation such as the absolute value of 2 minus x is greater than or equal to 3. Now here you look at this as the absolute value of 2 minus x, and you say to yourself, I would like it to read, how, Brenda?
The absolute value of x minus.
All right, the absolute value of x minus 2. Now may we simply rewrite that as the absolute value of x minus 2, Brenda?
Yes.
Yes, from what we said over here in our, let's come way over here, and our second idea, in which we had for every a and b belonging to a set of real numbers, the absolute value of a minus b is the same as the absolute value of b minus a. Okay? So let's then come back here to our example, in which we simply will rewrite it, and then this then is greater than or equal to 3, and go right to your number line. Okay? Let's see, now here is say 0, 1, 2, 3, 4, 5, 6, 7 to the right, and so on, and negative 1, negative 2, negative 3, negative 4, that should be enough. And what then is our starting point with respect to our graph, Doug?
2.
At 2, and how many units do we want to go away from 2 here? Someone hasn't said anything. Glenn?
Look at 3.
We want to go 3. Good. So here is 2, and we want to go 1, 2, 3 units away from 2, and that puts us at what point, Glenn?
5.
At 5, and what then do we want to have on our graph?
A closed circle at 5.
A closed circle at 5, and what else then?
And then a bar extending to the right.
And a heavy line extending to the right, indicating that the graph goes on forever in that direction. And now let's see, how many units do we want to go to the left? 3. 1, 2, 3 brings us over to this point, and of course that's at what number? Associated with that point is negative 1. And Michael, what then do we want to say about its graph?
You want to extend it to the left.
A heavy line to the left with an arrowhead on it, indicating that this is its graph. And let's then write the solution set. Notice that we are making the graph before we make the solution set. In fact, we're getting the solution set from the graph. And normally, you do your algebra and what have you, and then you come up with your solution set, and then you make the graph. Now, there is an algebraic approach that one could do in order to solve these problems, but in fact, I would rather that you ignore that and do it from this geometric approach, okay, right from the graph. Well, what then can we say? The set of all x's such that, and what then do we want to say here, Tom?
X is less than or equal to negative 1.
X is less than or equal to negative 1. And what's the crucial word in here?
Or.
Or, what then do we want to say, Charles?
X is less than, greater than or equal to 5.
X then is greater than or equal to 5, and I think this will be our solution set. Notice here, again, we must use the word or. Well, let's look at another example and see how that will go. Suppose we have the absolute value of 2x minus 3 is less than 5. And here now, for the first time, we have a number as a coefficient of x which is different from 1. And let's now think about our third example that we had, in which the absolute value of A times B is equal to the absolute value of A times the absolute value of B, and see what we may say. Let me write this as 2 times x minus, now give me a number here in which 2 times that number is equal to 3. And Bill?
1.5.
1.5, which we would rather write as 3/2, okay, is less than 5. Using our theorem then, this is the absolute value of 2 times the absolute value of x minus 3/2 is less than 5. The absolute value of 2 is 2. Let's then, what can we do to both sides of our inequality? We can, Brenda? Divide by 2. 2 is a positive number, so the sense of the inequality remains the same, and this then must be 5/2. Now, let's see if we can make the graph. And here we have, say, 0, 1, 2, 3, 4, 5 to the right, and so on, and -1, -2, -3, that should be far enough to the left, and so on, okay? Now, what's our starting point? Doug? 3/2, which we'll say is right here. And how far away from 3/2 do we want to go? And looking at our sentence, Don? 5/2. And 5/2, of course, is another name for 2.5. So there is a half, and now 2 more. So there's 1, 2. And from this point, we want to come over to here, of 5/2. And what number does that put us at? 4. And what then do we want at 4, Dick?
An open circle.
An open circle at 4. And now also we want to go to the left. How many units? 2.5. So there's a half. 1 and 2 puts us at this point, right, in which we want an open circle, and that's at -1, and then our sentence has to do with less than, so what then do we want as our graph, Michael?
A line between.
A heavy line between, and that then is its graph. Therefore, let me put it over here. We may write the solution set as the set of all x's such that, let me use the between this idea again. X is what? Less than 4 and greater than what number? Greater than -1. Okay, well, I think that's all that we need to do for today. So let me give you your assignment for next time. This will be a